Hi, John Valvano here, and in this video I want to review some of the definitions that apply to this class. And in particular I want to focus on the distinction between definitions that are applied to the transducer and those that will apply to the system, that we'll get to in a moment. Okay? So the transducer, as we choose it, we need to know about its range. So we want the range of the transducer to match the range of my specification, my system. Okay, and then similarly, we want the transducer to pass the frequencies of interest. Right, we want to be able to pass from the smallest to the largest frequency of the signal X that I'm trying to measure. Now, sensitivity is simply the plot of Y versus X, and in particular the slope of that curve. And we want it to be sensitive because the more sensitive the transducer, the easier it is to measure. One of the problems with transducers is they're not only sensitive to X, but they might be sensitive to something else. So for instance, if I'm measuring temperature, it might be sensitive to EM noise. If I'm measuring distance, it might be a function of temperature. And so we would like the transducer to have a very strong sensitivity to the signal of interest and a very weak sensitivity to other things. Okay? And that's sort of a qualitative understanding, but sometimes selectivity is what affects the system. In order to sell lots of them, make it accurate, we're going to need it to be stable, okay? And what that means is this transfer function, this y is a function of x, this transfer function remains the same across time. To make a lot of money, we would like this transfer function to stay the same across all transducers. That way the manufacturing and the production of the machine will be simpler. Okay? And linearity is a measure of this curve here. The linearity is, does it fit the y equals mx plus b curve? And in particular, does it, how much does it deviate, right? Is there an m and n, an m and b, right? Linearity is sort of the sum of this difference between the linear fit and the signal. To make the system work, it has to be robust. If it has to work in the environment, under pressure, vibration, temperature, humidity. Okay, so those are some transducer specifications. Here's a common fallacy about transducers or about systems, and that is a term called post hoc ergo prompter hoc, which means if the transducer, if we observe at the output of the transducer, a signal that looks like it is a function of A. I wash my car and it rains. It looks like every time I wash the car, it rains. So therefore, it looks like I have a transducer that's sensitive to rain. Well, as you might imagine, okay, the rain is caused by atmospheric conditions, okay, and therefore you got to be very careful when we think about selectivity, that if we're trying to measure one thing, we're not actually inadvertently measuring a second thing that just happens to, in our experiment, to follow along. So this is a very common mistake in machines that are a result of a poor design of how we tested it. All right, so that was transducer. Let's talk about the system. Again, we're trying to measure X, right? We're trying to measure X, we're displaying it on the screen somewhere. And so we use the transducer to measure Y, okay, to convert the signal into Y, and then we use either an analog to digital converter or a timer-based frequency phase period, pulse width, duty cycle kind of measurement. Okay? So that's a system where the input is truth and the output is measured. Now, if it's a control system, there's a feedback loop, and we'll get to that in subsequent course slides. All right. But we're looking here today on specifications of the system. Again, the input is truth and the output is what we've measured. Okay. So accuracy is common. It's a common specification of a system. Again, we input X, that's the true X, and we measure something that we hope is equal to the true X. And we have three basic definitions of accuracy. Average accuracy has units of X, where if this is in centimeters, if X is in centimeters, this is in centimeters, where we basically average the difference between the truth and measured. Sometimes we're interested in the worst case. And again, if X is in centimeters, this is in centimeters. And then to get a more statistical measure of accuracy, we could use standard error, which is the square root of the sum of the thing squared. Again, it would be in centimeters. Now, again, this is why I say it's important for you to not only use the term accuracy and measure it and test it, but define it. Okay, because you can see here's three definitions, here's four more, okay, just to make life complicated. Again, we're defining accuracy, which goes from the input to the output, or to the truth to the measured. And if we want accuracy in a percent, okay, we're going to somehow divide by the signal of that we measure. That'll give us a percent. And there are 7 definitions of accuracy. It is your job to choose the correct one that matters to your system, all right, to your problem, okay? And for example, if you're measuring both small signals and large signals, then this is the most appropriate one. Because if you're measuring both small and large, this will underestimate their error, giving you something that looks better, but it's not accurate. Okay, it does not represent how a system works. So again, your job is to work through these 7 definitions, look at how your system is used, and use not the one that gives you the smallest number, but the one that is most appropriate for your problem. This is obviously best when all the numbers are about the same, okay? When all the numbers are about the same, we'll use that one. Okay. Resolution, okay, is in this class, in my world, resolution is the smallest difference that we can detect. So for instance, if I make my input x1 and I measure this curve here, right? And then I increase my input by delta x, okay? And I measure this curve here. This is a probability mass function. So I repeat it 10 times, 100 times, 1,000 times, whatever, and get a probability mass function of the measurement, the number of instances that measurement occurred. And if I can distinguish between the solid and the dotted lines, I will then say my resolution is better than delta x, because I could resolve it. Okay? And one way to say is the solid curve different than the dotted curve is the student's t-test. Okay? So I'll calculate the t-statistic, which is the average of the one and the other, and the square root of the sum of the squares of the standard deviations. If you want more information on it, you can follow this link here. Okay. There's a pretty strong definition of resolution. A very simple, weak definition is something we'll call reproducibility. And sometimes we can't actually increase the input by delta x. That's not a possibility. But what we can do is make x a constant, right? If the input is a constant, and then we do a repeated measurement, again, n times. One equivalent definition of resolution is reproducibility, which is the standard deviation of that sample set. So it's sometimes easy to fix the input to a constant and measured over time. Again, that's reproducibility, which we sometimes use as a surrogate for resolution because it's easy to measure. All right. So in summary, what we have here are some specifications dealing with the transducer and others which deal with the system. And so if we wanted to, the transducer has to pass the signal of interest. And again, resolution is the smallest change that can be distinguished. Okay? And the things that affect resolution are noise, okay? Selectivity. So if some other parameter changes and the output changes, that's going to affect our resolution. Linearity, and I got an example of that in the next slide. And then we can improve the resolution by sampling over and over again and performing some averaging. And we'll got a whole slide on that in the future. Now remember, accuracy is the difference between truth and measured, and the things that affect accuracy are resolution. So those four will affect accuracy. And then if the transducer drifts, it's no longer accurate. And if I replace the transducer with something that doesn't work quite the same, it's no longer accurate. So we can sum up the differences between accuracy and resolution is, again, if we put in the input equals some true value, and I measure it 100, 1,000 times, calculate a probability mass function of the system, then the standard deviation is the reproducibility, which is our surrogate for resolution. But the difference between the two is accuracy. So let me give you an example of how linearity affects resolution. Okay? Here's a nonlinear transducer. First, what we got to do is chop off this part here and not use, this dead zone here we won't use. That's the non-monotonic range. Okay? So what I want to do is look at what, I know it's an unrealistic value, but it makes it easy for me to draw the picture. I'm going to say my resolution of this A to D converter is 0.5 volt. Okay? I know it's much better than that, but just for argument's sake, whatever it is, it don't matter. I mean, it'll be okay. All right. And then I want to draw two lines on my transfer equation that differ by 0.5 volt. Okay. So that's what the resolution of the AD converter means, that I can't distinguish between 2.0 volts and 2.5 volts. So I'm going to pick my points here, okay, and then draw two vertical lines. And now I can see at this portion of the range, this delta V of 0.5 volt converts to a delta L, that's my distance, a delta L, of about 2 centimeters. You see that? This guy down here is 2 centimeters. And now what I want to do is go to a different part of the range, okay? Because this is nonlinear, remember? This is a nonlinear system. And I'm going to do a different part. Now I'm going to draw this one and that one. Again, delta V is 0.5 volt, okay? But now, whoa, look at how bad this is. Now, my 0.5 volt here of A to D resolution maps itself into 30 delta L of 30 centimeters. That's pretty bad. So in general, to optimize resolution, optimize resolution and accuracy. I should have said, to optimize resolution and accuracy, I want to have a linear transducer. All right. Again, the bottom line in here is there are a lot of definitions. Make sure you define them before you use them. All right, enjoy.